Got a 60 kilogram box being pushed horizontally across the floor. The box is accelerating and it's got a coefficient of friction. So draw the picture, draw all the forces, pull out your friction, force of friction formula, some Newton's second law, that kind of stuff, and we got it. So here's the box, there's the mass. The weight is just mass times gravity, so 60 times 9.8, and that equals the normal force. Because the forces are balanced in this dimension, it's not going up or down. If it is accelerating to the right, that means friction is acting to the left. First one, what's the normal force? I've already been over that. What's the force of friction? Friction is mu times the normal force. And mu is 0.4, normal force is 588, so friction is 235. And maybe I should say negative 235 or 235 leftward, because I should really give a direction. What force is the student applying to the box? So now I need to use some Newton's second law and some of the forces. So what I've written here is net force equals mass times acceleration. That's Newton's second law. And net force equals the sum of the individual forces. So instead of writing these on two separate lines and then setting them equal, I'm trying to save space here. MA equals the sum of the forces, because those are two different ways of getting at net force. So there's the mass, there's the acceleration, and the non-canceling forces are the force of the student pushing to the right and the force of friction going to the left. These two cancel. That's not a force, that's just acceleration. So I've got 120 equals the force of the student minus the friction, which is 235, so the student's got to be pushing at 355. Number 3, skydiver, 60 kilograms, hung up on the 60 kilogram thing. Falling from an airplane with an acceleration that's upward, 7 meters per second squared. What's the force of air resistance? So here's my diagram. There's air resistance, or I'm calling it drag. This is the weight, 588 newtons, just like the weight of that 60 kilogram block. And here I've written net force, two different ways and set them equal. This is Newton's second law, and this is the sum of the forces in my diagram. Drag minus weight. So mass is 60, acceleration is 7, force of drag or resistance, that's what I'm looking for. There's weight, solve for drag, and you get 1,008. Number 4, this is, there's not much space for this. A fin. Those people are really good at keeping their forest floors clean. But apparently, according to this problem, they also like to jump off cliffs with balloons. They don't. I just made that up. So a fin jumps off a cliff with holding on to a rope that's attached to some helium balloons. The rope tension is 500 newtons. The mass of the fin is 80 kilograms. How long will it take the fin to reach the valley floor? So the end of this is a kinematics problem. We have y displacement. We have initial y velocity because the fin is just jumping off the cliff starting at 0 meters per second squared. And we need to find acceleration in order to find the time. But in order to get acceleration, we've got to do this Newton's laws kind of analysis. So here's the force of tension in the rope that's pulling the fin up, and this is the weight of the fin pulling the fin down. So I can express net force as fin's mass times acceleration, or the forces acting on the fin. The tension upward minus the weight downward. So there's the mass, acceleration, which we're looking for. This is the tension pulling the fin upward. This is the weight pulling the fin downward. Solving for A, I get negative 3.55. And once I've got acceleration, I can plug that into this displacement formula. The initial velocity is 0, so these terms go away. And I have 1/2 times acceleration, make sure that's negative, times t squared, don't forget the squared. So t comes out to 13 seconds. Number 5, I was thinking at first when I saw this was a harder problem than it was. I was thinking that Well, I don't even need to explain to you what I was thinking. You can see I had to erase a bunch of stuff. So there's Charlene. She's standing in a motionless elevator and the scale reads 600 newtons. So that just tells us her weight is 600 newtons. And I could just say weight equals mass times gravity. 600 newtons equals what mass times 9.8. Solve for mass, I get 61.2. I kind of wrote out some MA equals sum of the forces and arrived at the same thing here. What does the scale read as it accelerates upward? So now the elevator is accelerating upward, and with an acceleration of 3 meters. Upward or downward? Gosh, this was there were a lot of mistakes in this. I hope this wasn't a real test that I gave at some point. So, got my picture. This is Charlene. These are the two forces acting on her. The scale's pushing her up. That's what the normal force is. And her weight's pulling her down. And I can say her mass times her acceleration is equal to the sum of the forces acting on her. So here's her mass, which I found. This is her acceleration, 3 meters per second squared downward. This normal force minus her weight. And her weight I found in the first part, because your weight is what the scale reads when you're on a motionless surface on a scale. Or you could just take her mass, multiply it by 9.8, and you'd get that. So the normal force ends up being 416. So if you're in an elevator and it's accelerating downward, you're not going to press into the scale as much as when you're in an elevator that's sitting still. And if it's going up, you're going to press into the scale more, so it's going to read higher than your normal weight. This is another one where I thought it was a little harder than it was. I was thinking this is the point of this contact force problem is to expose you to something that's very similar to this, except instead of tensions and ropes and pulling forces, we've got pushing forces. But as it turns out, you don't really have to do a whole lot. I did more than I needed to. So the problem starts out saying two blocks are sitting on the surface with a mu static of 0.4. This should be mu kinetic of 0.4. You need to know the kinetic coefficient of friction, because what happens is a dog nudges the two blocks leftward and moves them at a constant velocity. So in the beginning, the dog's got to accelerate them, but it continues its nudge and they move at a constant velocity. What was I getting at? Oh yeah, if they're moving, then we need to know the coefficient of kinetic friction. I'm looking for the contact force between the blocks. So this is where the analogy between this problem and this problem comes in. Contact force is really like these tensions. It's just that these tensions are a pulling force. They're pulling the two blocks together. And the contact force is pushing. It's pushing the two blocks apart. The right block is pushing the left one to the left, and the left one is pushing the right one to the right. Equal and opposite action and reaction. This block is pulling the 6 kilogram up and toward it, and this 6 kilograms pulling the 4 kilogram down and toward it, or left and toward it. But it's the same kind of thing. It's if I analyze this entire system, these would cancel out and I wouldn't be able to solve for them. So eventually I want to write some equations where only one of these forces is acting. And down here, I would analyze the whole system and I'd get an acceleration and I'd go from there. But up here, I'm already given the acceleration, so I don't need to do that. That's what I started doing with all this mess you can see in the background. So the velocity is constant, which means the acceleration is 0. So I know the acceleration. I can just focus on the easy block, and the easy one is this one because it only has one force on it. This one's got the dog and the force of contact. This has just got the contact force. So I've separated out my two different ways of writing net force in this case. Net force equals mass times acceleration. That's the mass of this block times acceleration. So 0. There's 0 net force acting on it. As far as the sum of individual forces, there's the force of friction right here, So as this slides along to the left, friction is pushing this block to the right, and then there's also the contact force of this block pushing this to the left. So force of friction minus the force of contact. I'm calling this positive because it's to the right in my diagram. I'm calling this negative because it's to the left in my diagram. And I have to calculate the force of friction. So I need the normal force for that. And in order to get the normal force, I need the weight. And to get the weight, I need the mass, 2 times 9.8. That's where this 19.6 comes from. That's equal to the normal force. And the normal force multiplied by 0.4 is what gives me 7.8. So back to these equations. Net force is 0, and the net force is the force of friction, 7.8, minus the contact force. So if 7.8 minus the contact force is 0, then the contact force is 7.8. And I didn't need to find this force of friction or that weight or this normal force to do any of that. All right. 11 minutes. I think I'm pushing people's attention spans, but oh well. I'm going to do this last one. I feel like we've done this a lot, but maybe it's just me. Maybe I've done this a lot. So this kind of a problem, I'm not going to throw any surprises at you. There are going to be 3 steps you need to follow. First step, well, maybe 4. The first step is to draw all of the forces acting here and calculate out as many as you can before you start anything else. The second step is going to be to find an acceleration of everything in the system. It's all locked together. They're all accelerating together. Third step is to find the 2 tensions in the 2 different ropes. So for the first step, everything's got a weight, so you multiply every mass by 9.8, and that's where these 3 weights come from. And the block that's sitting here, it's got the most forces. It has a weight, but it's also got an opposing normal force, which is the same as the weight. And then there's going to be a force of friction acting on it. To figure out which way the friction acts, you have to look at these hanging weights and figure out which one's going to overpower the other. So this whole thing's going to go like that, because 6 is heavier than 2. And if this block moves left, friction goes right. Once I have that, I can calculate that friction by multiplying mu times the normal force. Mu is given here. The normal force I've got there is 15.7. And I'm drawing in my tensions. So the tension at both ends of this string pulls things toward the center. Same thing here. These are 2 different tensions because there are 2 different strings. It's possible that you could have the same tension in both strings, but it's not going to happen in one of these problems. Now, finding the acceleration, analyze the entire system. So all this stuff, this, the massless string, that, the massless string, and that, all together have a mass of 12 kilograms. I've condensed my 2 different ways of writing net force into mass times acceleration and the sum of the forces. So for the whole big system, its whole mass is 12. There's its acceleration. And there are 3 forces acting on it. There's this force, and there's this force, and there's friction. All the other forces but those 3 cancel out. The weight, the normal force, all the tensions, they cancel. And I'm calling this positive. I always just like to say clockwise is positive for this. So when I do this, and I solve for A, I get negative 1.96, which tells me it's going counterclockwise. So I've clarified the acceleration is 1.96 meters per second squared counterclockwise. To find the tension T1 over here, I'm going to isolate this little system. So now I can just focus on this block. I know the acceleration of that block because the whole thing's accelerating together. It's accelerating downward at accelerating upward 1.96 meters per second squared. So here we go. The net force acting on this system is equal to the mass times the acceleration. Notice that's positive because this is accelerating upward. And that equals the sum of the forces in the system acting on that block, T1 minus 19.6, this minus this. Solve for T1, you get this. And then compare. 23.5. That's stronger than 19.6. That's going to make this accelerate up. Good. That makes sense. T2, do the same thing except use this. So the mass is 6 kilograms. The acceleration is negative 1.96 because the whole thing's going like this. So this block's going downward at that rate. And then the individual forces are T2 minus the weight. T2 comes out to be 47. And see if that makes sense. We've got two forces acting on this, the weight of 58.8, the tension pulling up at 47. This is stronger than that, so this is going to accelerate down. Yeah, that makes sense.